and Theorem 1.4. Before we understand the theorem, let us understand what are co-prime numbers. So if you look at this rational number 1 upon 2, 1 can be written as 1 into 1 and 2 can be written as 1 into 2. And so the common factors between these two numbers are 1. If you look at this rational number 2 upon 4, then the factors of 2 are 1 into 2 and the factors of 4 are 1 into 2 into 2. So then we have two factors common between this numerator and the denominator, which is 1 and 2. If you look at 45 upon 21, you have 45 as 1 into 3 into 3 into 5, and this is 1 into 7 into 3. Again, you have two factors common, 1 and 3. 25 upon 50, you have three factors common here. 14 upon 27, only one factor, which is 1. So look at these two numbers and you can see the only common factor between them is 1. Here also you have only one common, 1 as a common factor, and therefore this rational number 1 upon 2 is in the form of P by Q, where P and Q are called co-prime numbers. And so we will say the numerator and the denominator are co-prime because the only common factor in their factorization is 1. Here also the only common factor in the factorization of this numerator and the denominator is 1. Okay? Now, in number theory, two integers a and b are said to be relatively prime or mutually prime or co-prime if they have no other common factor other than 1. So these 14 and 27 are co-primes, 1 and 2 are co-primes. Now let us understand the definition of rational numbers. A number R is called a rational number if it can be written in the form of P upon Q, where P and Q are integers and Q is not equal to 0. But there is one more condition which we should consider, which is this. When we say that P upon Q is a rational number, or when we represent P upon Q on the number line, we assume that Q is not equal to 0, and we also assume that P and Q have no common factors other than 1. That is, P and Q are co-prime. Now we begin understanding the proof of this theorem. So Theorem 1.4 says that root 2 is irrational. We have to prove that root 2 is irrational number. So let us assume to the contrary that root 2 is rational. Let us assume that root 2 is a rational number. If root 2 is a rational number, does that mean that we can write it in P upon Q form? Yes, it would mean that. Yes. So we can find integers a and b where b is not equal to 0 such that root 2 is equal to a upon b. Since it's a rational number, it can be written in P upon Q form. Here we are using a and b. Remember, a and b are co-prime. Because they are rational numbers, we will consider them as co-prime also. Now, does that mean that a and b has no common factors other than 1? Yes, it does. Since they are co-prime, they have no other common factor other than 1. 1 is the only common factor between them. Now, taking b to the left-hand side, we get b into root 2, that is b root 2 is equal to a. Now, to use Theorem 1.3, we need a square. So let us make this a square. If we square a, we also square b root 2 here. So squaring on both sides and rearranging, we get 2b square is equal to a square. Now b into b becomes b square and root 2 into root 2 becomes 2. So we have 2b square and a into a becomes a square. So we have 2b square is equal to a square. Now if 2b square is equal to a square, then is a square divisible by 2? So is this 2 a factor of a square? Yes. A square is divisible by 2. Yes. Therefore, 2 divides a square. Now, according to the theorem of 1.3, is a divisible by 2 as well? So if 2 divides a square, will 2 divide a also? Yes. Now, by theorem 1.3, it follows that 2 divides a as well. Therefore, can we say that a is a multiple of 2? Yes, a has to be an even number. It has to be a multiple of 2. So that's yes. We can write a as a is equal to 2c. That means it could be any number which is a multiple of 2. So we write c here as a variable for any integer c. So a can be written as 2c. Now substituting for a, so if I put this value of a is equal to 2c into this equation, we get 2b square is equal to a square. In place of a, we are going to write 2c. So we get 2b square is equal to 2c the whole square. That gives us 2b square is equal to 4c square. Now, substituting for a, we get this 2b square is equal to 4c square. Now, if I take this 2 to the right hand side, I get b square is equal to 2c square, because we will be doing b square is equal to 4c square divided by 2, and that will give us 2 ones are and 2 twos are, and so I have b square is equal to 2c square. Now, if b square is equal to 2c square, then is b square divisible by 2? Yes. This means that 2 divides b square. According to the theorem 1.3 again, is b also divisible by 2? If b square is divisible by 2, then can we say that b is also divisible by 2? Yes, we can. And so 2 divides b also. So 2 divides b square and 2 divides b also. Again using theorem 1.3, where p is equal to 2. That means the prime number is 2. And so if prime number divides a square number, the prime number also divides its square root. So 2 divides b square and 2 divides b. Therefore, a and b has at least 2 as a common factor. Now, has any contradiction arisen? Yes, it has. But this contradicts the fact that a and b have no common factors other than 1. So now this contradiction has arisen because of our incorrect assumption that root 2 is rational. This was not correct. We cannot assume this, because assuming this will create a contradiction like this. And therefore, we conclude that root 2 is irrational.